Hello, we are Bravo3, the Voyagers, and here is our PDR. First up, we got some team introductions. I am Beau Farnell, and I am the systems engineer. A fun fact about me is that I am in a rock band.
Hi, I'm Sarp, and I am the integration manager for Bravo3. A fun fact about me is that I play the cello.
Hi, I'm Aiden, and I'm the design manager for Bravo3. A fun fact about me is that I like to play golf.
Hi, I'm Sela and I'm the design engineer for Bravo3. A fun fact about me is that I play piano.
Hi, I'm Mufika and I'm the Subtopic 1 manager. A fun fact about me is that I like to bake in my free time.
Hi, I'm Blythe and I am the Subtopic 1 technician. A fun fact about me is that I play piano and guitar.
Hi, I'm David and I am the Subtopic 2 manager. And a fun fact about me is I play the drums.
Hi, I'm Logan, and I'm the Subtopic 2 technician. A fun fact about me is that I play basketball.
Hi, my name is Elena, and I am the Subtopic 3 manager. A fun fact about me is that I am a theater kid.
Hi, I'm Vijitha, and I'm Subtopic 3 technician. A fun fact about me is that I like to read.
Our patch is decorated with a glowing moon against a dark blue background, with 10 white stars to represent each member of our team. It also contains the team name we created, Voyager, which combines our given name and our desire to complete our mission. The words E Luna ad Martem means from the moon to Mars in Latin, which describes the goals of the Artemis mission.
Also, huge props to our amazing NASA consultant, Mr. George Salazar, and another big shout out to our game moderator, Miss Patty Ashley. Thank you both so much. Alright, let's hop into it. The ultimate goal of our mission is to create a spacecraft which can deliver our payload from Earth to lunar orbit. To achieve this, we must also make the craft safe and habitable, give it ample amounts of propulsion to reach its destination, and create a timeline, capsule design, and communication for the system, as well as coordinate with other teams to determine the payload. Oof. We plan to do multiple flights as the mass of materials is immense, and not all materials are immediately needed. We initially plan to send the first 4 astronauts once the HALO, habitation unit in lunar orbit, is complete, and the second group of 4 astronauts once the habitat on the lunar surface is complete.
Bravo's mission was flying to lunar orbit. This meant that we were in charge of delivering all materials and astronauts required for the mission from the Earth's surface to lunar orbit. Our first subtopic was interplanetary spacecraft design for lunar orbit. Our second subtopic was to develop and identify a prototype in-space propulsion to reduce time for our lunar mission. Finally, our third subtopic was risk assessment and rationale. We chose these 3 subtopics from our 4 subtopics because we found them the most engaging and relevant to our mission, especially considering that the 4th option, landing on the lunar surface, was not part of Bravo's mission.
Our mission was to create a human-rated spacecraft that is capable of interspace travel, so interplanetary spacecraft design is a key area of research to create a suitable design.
We based our capsule off of the Orion spacecraft, which is built of 3 components: the Launch Abort System, or LAS, the Crew Module, and the Service Module. LAS will activate when there is an emergency, and it will position the crew for safe landing. The Crew Module houses astronauts. The Service Module includes water and oxygen supply, energy, with the solar arrays attached, and in-space propulsion.
The design can be broken into more specific systems for safe human transport to the moon. Our spacecraft will use an inertial navigation system made of gyros, accelerometers, and a central processing unit to measure relative location to the last position. The spacecraft's heat shield has a silver thermal coating bonded to back shell tiles just like on Orion. To protect from radiation, our capsule will be covered in a layer of polyethylene and other hydrogen-rich shielding. The water and waste system utilizes various forms of recycling, and we plan to have a small space garden. The electricity system is powered by solar panels, and we have a storage area for experimentation and tools provided by other teams. The redundancy system, based on automated computer intelligence, will take over during technical emergencies to bring astronauts to safety. We also need a propulsion system, which is covered in more detail in the following subtopic. Our communication system will use LunaNet Moon Wi-Fi as determined by other teams.
With a better understanding of our craft's compartmentalization, the complexity of our mission is understandable. To make sure operations run smoothly, we created a mission timeline based on the Mars Odyssey launch sequence. Here's the timeline. 1. Build individual parts and stack them on the launch pad. 2. Fire engines to launch the spacecraft. 3. At an altitude of about 18 kilometers, the rocket boosters detach. 4. The first stage/main engine separates at about 125 kilometers. 5. The second stage is fired about 13 seconds after the first engine cutoff. 6. The second stage is cut off and the craft is now in low Earth orbit. 7. The third stage is ignited and the craft detaches from Earth's orbit towards the moon. 8. The craft uses cruising and inner space propulsion for about 3 days to reach the moon. And 9. Inner space propulsion is used to enter lunar orbit and attach to the lunar orbiting base. From there, the intended landing site is Shackleton Crater, but further missions are handled by other teams.
The second subtopic mission focuses on the prototype propulsion system that will most safely and efficiently get us to lunar orbit. For this mission, we decided upon a solid-liquid hybrid propulsion system. This system includes a solid fuel that is burned and a liquid oxidizer that is pumped onto the fuel, as you can see in the diagram to your left. For the fuel, we chose hydroxyl-terminated polybutadiene, and for the oxidizer, we chose liquid oxygen. Additionally, we decided to use the SLS rocket architecture, which you can see in the bottom left.
NASA spends millions and billions of dollars making sure their space missions run smoothly. They do this to keep the astronauts safe and to make sure they reach their objectives for their mission. And they do this all following the process called risk assessment.
There are 3 key questions to ask about risk assessment. What could go wrong? What's the possibility of it happening? And what are the consequences?
There are an infinite amount of things that could go wrong during a mission, and it is the responsibility of engineers to figure as many as possible. Some of these things include radiation damage, especially during geomagnetic storms, so it's critical to have a working shield and a backup just in case. Loss of communications is something else that could happen, like seen in the Ariane 5 rocket launch that ruined the orbit of the satellite. Having working backup communications is essential to prevent something like this from happening in the future. Technical, calculational, and measurement errors are also something that are very common, so having many eyes looking at the mission can help decrease these mistakes.
Another example of what could go wrong is hybrid propulsion failure. If the fuel and oxidizer do not mix together, it can cause the shell to fail and shut down. However, there is a way to prevent it. It has a built-in engine that is robust and less sensitive, making it less likely to blow up. However, the Challenger was not so lucky. It blew up because the external fuel tank mixed together when launching. One way it could have possibly have been avoided if there was a temperature control that helped maintain the fuel from overheating before they were mixed together.
Some ways to avoid damage to the spacecraft or to the mission is to do a lot of testing. Making replicas of parts of the spacecraft and testing them in extreme conditions, such as being tested in wind tunnels, being crashed, dropped from a tower or into water, heated to extreme temperatures, and being vibrated are essential to making sure the spacecraft performs correctly during the mission. In addition, it is also important to have a mock run of the mission with the astronauts so they know how to perform when the day comes. Also, learning from mistakes of past missions is another thing that we could do to make sure this spacecraft is ready for launch. 3D wireless scanner was created after the Columbia crash to detect damage in heat insulation tiles, which we could use for our spacecraft in addition to multiple other pieces of technology. Also, having cameras and sensors all over the spacecraft when testing parts of it can help bring back helpful information that engineers could use to help better the spacecraft and the mission.
With these research-guided decisions in mind, it was our job as a design team to create a solution to the design challenge. With a focus on flying from the Earth to the Moon, our design challenge was to create a human-rated capsule that can safely travel to lunar orbit while also carrying additional loads.
When it came to designing, we followed the research and advice given by our own team while also coordinating with the other teams through our system engineer. The options we struggled with most in our design included deciding on a cargo area as well as deciding on the different types of electrical energy systems we could use. A cargo area was necessary to fit the materials needed by the other teams A through I. Its pros included greater storage space and more flexibility in what we could take to the moon. Its cons included creating more mass and needing more power to compensate for it. We found it best to still add the cargo area, but make it within a relatively small size to ensure that the spacecraft could still carry the astronauts.
The types of electrical energy systems we chose to decide between were solar panels and batteries. The solar panels, although very advantageous in space because they use energy from the sun, also take up more surface area. The batteries, which takes up less space, can store energy but use their energy quicker. This is not ideal for a trip to the moon, so seeing that solar panels could continuously use the sun's energy, we chose to use solar panels in our design.
To better focus our design, we drew the interior and exterior of our spacecraft. We were able to recognize the importance of redundancy, which is the adding of multiple features for emergency purposes. We wanted to stay as true to our drawn prototype as possible. However, we were restricted to materials we already had at home, so we decided that cardboard, paper, and aluminum foil would be essential to our model because we had access to large amounts of these.
While building this model, we faced and overcame a multitude of challenges and revisions. These challenges started with finding household items that would correctly portray the model of the crew module, although our resources were scarce and limited to my household. Size was a challenge from the start. As we made our selection, we were mindful to fit all the objects required and discussed. At first, we thought about using a plastic cup and a lampshade, but after running into difficulties with size and cutting into the lampshade material, we needed another option. We decided on cardboard because it was malleable and found a cork hot plate that fit the diameter of the capsule. While we felt that the capsule shape was coming together, we decided to focus on a cargo area below the capsule. After careful consideration of what item would best fit true to size and form as an addition to the capsule, we decided on a plastic coffee container. Wrapping the cardboard in aluminum foil for the radiation protection was an impromptu modification from the original design since it was originally inside the capsule. In the beginning, I wrapped the storage container with black construction paper, but decided to change to black duct tape because of the insufficient resource of the construction paper. We used pieces of cardstock for solar panels, gluing blue paper to one side to emulate them, but later added clear tape to hold the product together. The next challenge we faced involved connecting the solar panels to the cargo area without having them sag. We ended up removing the capsule from the top and creating holes to place hard plastic support beams to secure the weight of the solar panels. The inside of the capsule was completed by using Legos for the environmental control and CO2 scrubbing systems, while using construction paper, duct tape, felt, and clay for all the other components. We had to change the design of the chairs because the original chairs were too big to fit in the capsule. We neglected to take the arc of the capsule into consideration when developing the layout, which was easily corrected once identified. On the outside of the capsule, we added the antennas and the windows, finalizing it. Finally, to represent the propulsion system, we painted 5 cups and added yellow and red tissue paper to represent firing of the engines.
Our additional features include a cargo area that can carry about 1,500 kilograms, a water dispenser to provide for the astronauts, an exercise machine to keep the astronauts healthy, and food supplies for the astronauts. Additionally, the interior of the model has removable parts which act as our launch abort system for emergencies.
Nevertheless, the Bravoiders were not entirely independent in what we were doing. We collaborated with the other teams a pretty significant amount because we were responsible for getting all the things they needed from Earth to lunar orbit, such as Charlie's habitation unit. All of the team's gear totals at least 12,500 kilograms, and to move that much mass would take around 8 trips, assuming we can transport 1,500 kilograms per launch.
Additionally, we decided to coordinate our lunar communication systems via LunaNet Moon Wi-Fi and collectively selected our total number of astronauts and when to launch them.
Here's our bibliography. It has the references that we used to make this PDR. And now, thank you so much for taking the time to watch our preliminary design review. The Bravoiders hope you have an excellent rest of your day.